Hello friends, welcome to session 17 on support vector machines. Okay, we are going to be doing two lectures on support vector machines. This is the first part and it will deal with hard margin use cases. Okay, I am going to explain in just a moment what that means. Let's get started. Okay, so here is the agenda for today. We are of course going to be talking about support vector machines, what they are, what they do. We are then going to set up the optimization problem for support vector machines. SVM is of course the short form for support vector machines. We are going to set up the optimization problem. And finally, we are going to apply what's called the KKT method, the Karush Kuhn-Tucker method for solving the optimization problem for SVM. So that is the agenda for today. So what are support vector machines? What are support vector machines? Now, support vector machine is a technique for binary linear classification. So we have been doing binary linear classification for a while now, and SVMs are yet one more technique for binary linear classification. The SVM technique has a very clear interpretation on what it seeks to accomplish. Okay, so the definition of a support vector machine is very clear in terms of how it differs from the other binary classification techniques and what it seeks to accomplish. Okay. And finally, mathematical packages are available for its implementation. So off-the-shelf libraries are available in whatever framework you are using that will allow you to implement support vector machines. And this is what makes them popular. They are a technique that is very commonly used in practical scenarios for binary linear classification, and therefore they are an important topic of study. Now, I will explain this name later, okay, support vector machines. This is a fairly peculiar name. I will explain why this name comes about. I'll explain it later once we are at the end of our lecture. And in this lecture, we will only deal with separable data. Okay, so I said we are going to be doing two lectures on SVMs. In this lecture, we are going to be doing hard margin SVMs, which refers to the scenario where your training data is linearly separable. Okay, so we are going to be dealing with only linearly separable data in this lecture. In the next lecture, we'll extend what we are doing today to non-separable data. So hard margin SVMs today, only separable data today, followed by non-separable data in the next lecture. This is just a diagram that shows you what exactly I mean. Your training data is linearly separable, and that is what a hard margin SVM deals with. Okay, so since we are talking about yet one more technique for classification, let us just sort of step back and see broadly how classification techniques usually work. In all of these techniques, firstly, you need to define a concept of distance. Okay, so distance in various techniques, it could be the Euclidean distance between points, or in the case of logistical regression, you came up with the ideas of probabilities, and the concept of distance over there was linked to the idea of probabilities, right? The difference in the probabilities. So in every classification technique, you need to begin with the concept of a distance. I would say not just in classification techniques, in pretty much every AI algorithm, at somewhere deep down is a concept of distance that you have defined between data points. The next thing that we do is we usually define an objective function or an error function that is to be minimized. And sometimes there are constraints, as we saw in the case of regularization. So the objective function may differ, or the error function may differ from one technique to another. In the case of, the earliest technique that we saw for linear classification, we used the so-called hinge function. In the case of logistic regression, it was a more complicated error function that was a function of the probabilities, right? So we define an objective function that has to be minimized in pretty much every technique. And finally, we run an optimization package. We run an optimization package to minimize the error function on the basis of the training data. So you're given training data, you have defined an error function, and you use some optimization technique that is suitable for that error function. You run that optimization package to minimize the error function by feeding it the training data. So you try to minimize the error function on the training data. So this is how all classification techniques usually work. Okay then. So how do the results of these different techniques differ, right? Of course, using different techniques will result in different class boundaries. So for example, if you had data looking like this, using a different technique might result in a different class boundary. Okay. Now, depending upon the data, these class boundaries would differ depending upon the data as well as the technique. But that is essentially what is going to happen. Now, even if you had linearly separable data, and if different techniques gave you different class boundaries, they could still be different from each other. So for example, 3 different techniques may end up giving you these 3 different class boundaries, all of which give you 0 in sample error, right? So the error on the training data is 0 for each of these. The question that you would now ask is that although EIN is 0 for each of these, is there something that differentiates these from each other? I mean, is there a way for you to say that one of these is better than the others? And naturally, the question that you would ask is which technique can give you better generalization. Better generalization means lower E out, right? Lower E out, lower out of sample error. Remember, we have said all along that E in is not our primary target. E out, the out of sample, is our primary target. And therefore, if you ended up with different class boundaries, perhaps there is one of them that gives you the best generalization. That means gives you lower E out. And therefore, you want to find a technique that can give you the best generalization. Okay. Now, intuitively, what you would assume is that the class boundary that has the largest margin would give you the best generalization. Now, I have defined a new term over here called margin. So let us see what I mean by this margin. You have this data, okay, and let us say you have a class boundary that you came up with using some technique. Create 2 parallel hyperplanes. Create 2 parallel hyperplanes to this class boundary, which is itself a hyperplane, so that these 2 pass through the closest points on either side of this class boundary. So let us say this particular blue point is closest to this class boundary, and therefore you draw a parallel hyperplane passing through that blue point. And similarly, on the yellow side, let's say there are these 2 points which are the closest to this class boundary, and therefore you draw a parallel hyperplane through those 2 points. I define margin as the distance between these 2 hyperplanes. Okay, these 2 hyperplanes. So this is the margin. So essentially the margin is the distance between the 2 parallel hyperplanes, parallel to your class boundary, parallel to the boundary that was returned by your classification technique. The distance between those 2 parallel hyperplanes is your margin. And what are these 2 parallel hyperplanes? They are the ones that pass through the closest point or points on either side. Okay, and of course they are parallel to this class boundary that your classification returned. So if you could identify the class boundary, that has the largest margin, that yields the largest margin, that would probably give you the best generalization. So stare at this for a while. What I'm trying to say effectively here is find that class boundary, find the separator that has the largest, that has the largest distance from the closest points on either side, and you sort of try to make them equal. So you put this thing right in the middle, because to you are treating both classes as basically the same in the sense of their importance. So this is the class boundary that I would be looking for, and it is the one that has the largest margin. Why does this intuitively make sense? Well, first of all, we know that data generation process can be noisy, and a larger margin will naturally be more accommodating of the noise. So for example, if I was maximizing my margin, and let's say if a yellow point ended up over here, I would still classify it correctly. And let us say a blue point ended up over here, I would still end up classifying it correctly, because I have given adequate margin, the best possible margin on both sides, right? So therefore this is likely to generalize better. The other general principle that you should keep in mind is that logistic regression, which we studied earlier, showed us that the probability of error reduces away from the separator as the general principle, right? We saw that the probability of error goes down as the distance from the separator increases on either side, and therefore you want a scenario where your separator is such that all your points are maximally away from this separator to begin with. So if the distribution of your out of sample data mirrored the distribution of your training data, they too would fall as far as away as possible, and therefore the probability of error would be reduced, right? So that is the general principle I am hinting at. We will talk about this a little bit more theoretically towards the end of this lecture, but for now I think it is acceptable to say that intuitively the class boundary that maximizes the margin is the one that is likely to give you the best generalization, and therefore I would like to find the class boundary. I would like to find a class boundary that has the maximum margin. Okay, great. So what then is an SVM? The SVM is a technique to determine the classification boundary with largest margin. Remember, we said that SVM has a clear interpretation. This is that clear interpretation. SVM is a technique that gives you the best generalization by choosing the classification boundary with the largest margin. Okay, so that is what it does. Now, we are going to, in this lecture, we are going to draw all of our diagrams in 2D, of course, in 2 dimensions. And that sometimes hides the complexity of the problem. Okay, it becomes, things start looking fairly simple in 2 dimensions. And therefore, I want to spend a minute going to 3 dimensions. Of course, 3 dimensions is also very less. In reality, the number of your independent variables could be in hundreds or thousands. But even in 3D, it starts giving you some inkling of, how complex this problem can be. So how do I visualize in 3D? Now, I was looking for, the illustrative examples to illustrate, to show this thing in 3D. And the best example I came up was, looking at 2 bushes, adjacent bushes. So if you walk in a park or go to a garden and you see 2 bushes that are not touching each other but sort of near to each other, treat them as your 2 classes, the training data in 2 classes. And then you want to find the hyperplanes that maximize the margin. Okay, and you will see the number of directions or orientations there are that, that you have to sort of analyze to find the best to find the highest margin. So you can try this exercise. Spend a moment in the garden looking at two adjacent non-touching bushes. Probably a crowd will gather around you to see what exactly you are staring at, but it will give you some idea of how this problem is all about orientation of the hyperplanes. It's about if the problem of choosing the hyperplanes with the widest margin is a problem of choosing the right orientation. You will quickly see that in 3 dimensions. I tried to do that same exercise with two feeble looking bushes, and I held 2 pieces of paper and tried to see, what would maximize the margin. And after some attempts, I was able to come up with the orientation that sort of maximize the margin. But that is the way to visualize this thing in 3 dimensions. And like I said, it's all about orientation. You have to essentially choose the right direction of the separating hyperplane. Okay, so now we are going to pivot to the math. Now that we know intuitively what we are seeking to accomplish, we are going to pivot to the math. And what we say is that we want to find the linear classification boundary W, hyperplane represented by W, that has the widest margin. So again, an attempt to draw this in 3 dimensions. You had 2 classes, blue points and yellow points, and this was your separating hyperplane, W transpose X equal to 0. To refresh our notation, W transpose is W0, W1, W2 up to Wm. M is the number of independent variables, and your X vector is x1, x2, x3, xm with a 1 that multiplies W0. Because remember, the equation of the plane is Wm xm plus all the way to w1 x1 plus w0. So there is a 1 implicit over here which goes in the x vector, and this is your w0 right here, right? So the 1 multiplies the w0. We've done this, we've used this extensively. For the purpose of SVM, what we are going to do is we are going to engage in a minor change of notation. Okay, this change of notation is purely for the purpose of convenience in the derivation of the SVM that is going to follow. Okay, so purely for reasons of convenience, we are going to engage in a slight change of notation. We are going to pull out the constant term from W. So for this lecture, just for this lecture, my W vector is going to begin with W1 and go through Wm, and my X vector does not have that 1 constant in there. So therefore, the equation of my hyperplane, instead of being W transpose X equal to 0, becomes W transpose X plus B equal to 0, where B is really my W0. So why am I renaming W0 as B? It is just to show that it is distinct from the W, because the treatment that it is going to get during the SVM derivation process is going to be different from the other W parameters. So therefore, I am going to call it by a different letter B. But at the end of the day, this is just simply a change of notation. Now, one thing that you of course know is that this equation of the hyperplane, or even this one here, can be scaled, right? I mean, you could multiply both sides by any constant, and that would still be the equation of the same plane, right? So I multiply both sides by 100. If I multiply each of the W's by 100, it doesn't matter, because at the end of the day, 100 times W transpose X equal to 0. Similarly, in my new notation, I could multiply each of the W's by 100, multiply the B by 100, and it would still be the equation of the same hyperplane, right? This could be any constant right here, because any constant type 0 is 0. So there is essentially a redundancy in the sense that the equation of a single hyperplane can be, there are infinite representations for the equation of the same hyperplane. And therefore, if you want to find the best hyperplane, you do not want that redundancy. You want to nail things down, right? So you would somehow like to take care of this scaling, whereby there are infinite equations for the same hyperplane. Okay, let's talk about scaling now. Okay, and I have sort of put a red star over here just to indicate how important scaling is. It's one of the more important ideas because the scaling here is a little bit peculiar and we need to understand why it is being done in this peculiar manner. But let's understand how the scaling operates in SVM. Now, because of linear separability, if you had a separating hyperplane W transpose X plus B equal to 0, for all points xi in your training data, modulus of W transpose xi plus B would be greater than 0. So this is your hyperplane right here. This is your separating hyperplane right here with the equation W transpose X plus B equal to 0. If you were to evaluate this for any point in the data set, the modulus of W transpose Xi plus B would be greater than 0 because the distance of each point from this separator is greater than 0, right? Now, let us say you had the nearest point XP. The nearest point was XP and there could be one or more nearest points, but there will always be at least one nearest point. And let us say that a nearest point was XP. Here I have indicated it with this yellow, this yellow dot right here. For that nearest point XP, let us say W transpose XP plus B modulus evaluates to some number KP. Okay, so it's going to be greater than 0. Kp is going to be greater than 0. And when I plug in the values, the coordinates of xp into the equation of this separating hyperplane, I get it evaluates, its modulus evaluates to some positive quantity xp. Now, we know that the general formula for the Euclidean distance of any point xi from this hyperplane is given by this equation. The Euclidean distance di is equal to modulus of W transpose xi plus b. You plug in the coordinates of xi, you take its modulus and divide it by the norm of this vector w, right? So this is the general formula for the Euclidean distance of any point from this particular hyperplane. This is high school geometry. Here is how we are going to do our scaling. Our scaling for every hyperplane is going to be based upon the point nearest to it. So for example, for this hyperplane, if xp was my nearest point, I am going to scale the values of w's and b such that W transpose xp plus b modulus is equal to 1. It could be plus or minus 1 depending upon whether the nearest point is on this side or the other side. But I am going to scale so that its modulus becomes equal to 1. Okay. So in other words, what I am saying is that Kp equals to 1. With this scaling based on the nearest point, the Euclidean distance from the nearest point xp of this hyperplane is simply 1 divided by norm of w, right? So this is the Euclidean distance. I have simply, instead of xi, I put xp over here and I scaled so that this is equal to 1. I set kp equal to, I divide the values of w and b by kp so that this becomes equal to 1, and therefore the Euclidean distance of the nearest point from this hyperplane becomes equal to 1 over norm of w, right? This is the scaling that we are going to implement while formulating the SVM optimization. Now this is a little bit peculiar. It would have been so much easier to say that all w should basically be unit vectors, right? I mean, that would be the obvious scaling to perform, but as we will see in some time, this sort of scaling actually simplifies the formulation and therefore helps the optimization. You need not have scaled anything at all, like I said earlier. You need not scale anything at all, but then you would get something in the denominator, you would get a lot more parameters, and the formulation of the problem would not be very neat. So this scaling is essentially being done to simplify the formulation of the problem. Okay, and that is why it is important. It is peculiar. Because the scaling is important, let us understand this in little greater detail. Okay. Now, the equation of any plane P1, let's say you are given a plane P1 here. P1 is, let us say, in 3 dimensions, ax plus by plus cz equal to k1, right? Where k1 could be positive or negative. The direction vector perpendicular to the plane is given by these coefficients a, b and c. This you know. So my direction vector w, this is w, it's perpendicular to the plane P1, and this direction vector is given by these coefficients a, b, c from the equation of this plane. The relative values of a, b, c of course determine the orientation of w, and therefore the orientation of the plane P1. So as you change the relative values of a, b and c, this plane sort of tilts in various directions. Let us consider another parallel plane P2 on which a point xp lies. So xp is a point which is not on plane P1. It lies on plane P2, which is parallel to plane P1. So I have drawn, this is the point xp right here. This is plane P2 parallel to plane P1. So therefore the direction vector w is also perpendicular to P2. And dp, let us say, is the Euclidean distance between of the point xp from the plane P1, which would of course be the perpendicular distance between P1 and P2 as well. Let us say the equation of P2 was ax plus by plus cz equal to k2. P1 and P2 would only differ in this constant, right? So in P1 it is k1 and for P2 it is k2. The Euclidean distance of xp from P1, which is the same as the distance between P1 and P2, is given by dp equal to k2 minus k1 upon square root of a square plus b square plus c square. We know this, and this is nothing, the denominator is nothing but the norm of the vector w, right? So this is coordinate geometry that we are well aware of. Now let us compare multiple planes. Okay. So this is my plane P1. Okay. This is my plane P1 that I had drawn earlier. And the distance of this point xp from plane P1 that we saw earlier, we computed this earlier, was k2 minus k1 upon square root of a square plus b square plus c square. Okay. Now, this of course is the Euclidean distance of the nearest point to plane P1, dp. I could normalize the values of ABC in the equation of the plane, so that if I divide the numerator and denominator by the norm of k2 minus k1, I will get the same dp as being equal to 1 over square root of a dash square plus b dash square plus c dash square. This is the scaled version of the plane. This is the scaled version of the equation of the hyperplane. But just because I scale the equation of the hyperplane doesn't mean that the Euclidean distance of that point from that plane is going to change. Here is another plane which is not in the same orientation, and xq is a point that is nearest to this other plane P2. Okay, and dq is, let us say, the Euclidean distance of xq from pq. Let us say that is k3 minus k4, some other constants, divided by m square plus n square plus o square, right? So the equation of P2 was mx plus ny plus oz equal to k3, for example. I could normalize the equation of plane P2. So that I can write the Euclidean distance of that point Q from this plane P2 as 1 over square root of m dash square plus n dash square plus o dash square, right? Now, very important to notice that A, B, C over here have been divided by K2 minus K1, okay, whereas M, N, O over here have been divided by K3 minus K4. So the way the equation of every plane is going to be scaled, is going to depend upon the distance of the point that is nearest to it. XQ could be close to P2, XP is close to P1. Okay, so the nearest point for every hyperplane could be different. The distance of the nearest point to each hyperplane could be different, and therefore the scaling of each hyperplane equation is going to be different. However, when you do this scaling across all hyperplanes, the maximum distance, d max, which is the distance of the nearest point to each hyperplane, is going to happen when the denominator is minimum, or in other words, the norm of vector w is minimum. This is what the scaling in SVM really does. I'm going to take a small example while comparing two directions. Okay, let us say there are 2 points over here of color yellow and blue. The yellow colored dot is at x equal to 7, the blue colored dot is at x equal to 11. Now let us say if I had a hyperplane right here. Okay, if I had a hyperplane right here which is close to the point x equal to 7. The equation of that hyperplane would be ax plus b equal to 0, right? And because x equal to 7 is its nearest point, let us see how I am going to scale it. Like I said earlier, I could multiply a by 100, b by 100, and it would still be the equation of the same hyperplane. But let us see how I am going to scale it. Because 7 is the nearest point, I plug in x equal to 7 and set its modulus equal to 1. Right, with nearest point x equal to 7. I remove the modulus, I put a minus sign over here because this point is on the origin side of this hyperplane, right? So this is going to be minus. And I evaluate for b, I get b equal to minus 1 plus 7a. I plug the value of b back into the equation, I get ax minus 1 plus 7a equal to 0, which means that x equal to 7 plus 1 over a. So the equation of this hyperplane is x equal to 7 plus 1 over a. Now as a reduces, this hyperplane moves further and further away from the point x equal to 7, and the maximum distance is accomplished when a equal to 0.5. Okay, why cannot a be made less than 0.5? You can stop the video over here and try to answer this question. Clearly from this equation over here, as the value of x reduces, as the value of a reduces, the value of x starts increasing. That means this hyperplane starts moving towards the right. The distance from that point starts increasing. And the maximum distance is accomplished when a becomes equal to 0.5. Now, why cannot I make a equal to 0.4 or 0.1? You answer that question. You can stop the video and answer that question. Similarly, let's try to go from the other side. Let us say my closest point was x equal to 11. Let's say this is my hyperplane. I substitute x equal to 11. I remove the modulus and do not put a plus sign on the 1 because this point is on the other side of the origin for this hyperplane. 11a plus b equal to 1 and x equal to 11 minus 1 over a. Right? Now, as you reduce the value of a, this hyperplane is going to move further and further away from this point. Right? Further and further away from this point. And the maximum distance again is accomplished when a becomes equal to 0.5. Right? So hopefully you guys have answered the question on why I cannot make a less than 0.5, because let's say if I was working from point x equal to 7, if a became less than 0.5, point x equal to 7 would no longer be my closest point. My closest point would be this, and then I have to do my calculations based on x equal to 11. Similarly, if I began with x equal to 11, when I reach a equal to 0.5, I cannot reduce a further beyond that, because then x equal to 11 would no longer be my closest point. So you see how it works, right? You have to look at the closest point, which differs for every hyperplane. Okay? And that is why the optimum hyperplane in this case is going to settle right in the middle of these 2 points. Now, let us say I had another direction, right? The distance between these 2 points, the Euclidean distance between these 2 points was 4. Here I am taking a smaller Euclidean distance. And I am just going to do the exercise for, for this hyperplane with treating y equal to 10 as my closest point. Let's say the equation is my plus n equal to 0. I plug in y equal to 10. I get y equal to 10 minus 1 over m, right? And as m reduces, this hyperplane moves further and further down, and the maximum is reached when m equal to 1, right? Beyond m equal to 1, if you reduce m any further, the nearest point becomes this one. It's no longer the blue point, right? So as you can see over here, as you can see in this example, in this out here, the maximum distance is accomplished when a equal to 0.5. Here maximum distance is accomplished when m equal to 1. Out of these 2 points, out of these 2 values, 0.5 is of course less than 1, which means that this hyperplane is going to be a better separator in terms of maximizing the margin compared to this separator, right? So that is how the underlying mechanism of the SVM works. So here is the summary of scaling. Each candidate plane has a nearest point out of the training data. Equation of each plane can be scaled keeping in mind its nearest point, right? Each plane has a nearest point. The nearest point for each plane could be different, but the equation of every plane can be scaled keeping in mind its nearest point. The scaled plane with the smallest norm is the one with the largest Euclidean distance from its nearest point, right? I just showed that to you with an example just now. Once you start scaling the planes in this manner with respect to their nearest point, the scaled plane with the smallest norm in the denominator is the one with the largest Euclidean distance from its respective point. So therefore we find such a plane under the constraint that it classifies all the training points correctly. That is the formulation of the SVM problem. In other words, we maximize 1 over the norm of W. This we said was the Euclidean distance of the nearest point from the equation of the scaled plane. So you want to maximize this. You want to maximize the Euclidean distance subject to W transpose X plus B modulus being greater than or equal to 1 for all points xi in the training set. Why greater than or equal to 1? Because the minimum we set as 1. For the nearest point, we set this equal to 1 for every hyperplane. Therefore, for every other point, if you are looking at one particular hyperplane, for every other point with respect to that hyperplane, this will be greater than or equal to 1. W transpose X plus B will evaluate to greater than or equal to 1 for all points xi. I forgot to put an I over here in the training set. So, this is what we are going to do. So now let us write down the constrained optimization problem that we solve for the SVM. Our goal is to maximize the margin. We maximize the margin by maximizing the distance of the hyperplane from its closest training point. To do that, we've just gone through the derivation to show that you have to maximize Euclidean distance, which is equal to 1 over the norm of W, subject to the minimum of W transpose Xi plus B being equal to 1. In the previous slide, I said this would be greater than or equal to 1. which is another way of saying that the minimum of this has to be equal to 1 over all points xi in the training set. So this is the constraint optimization that we need to perform. We are going to write this problem a little bit differently, but in a way which means exactly the same thing. What we are going to do is, instead of maximizing 1 over norm of W, we are going to minimize W transpose W. Here W is in the denominator, here it's in the numerator. We are going to minimize W transpose W divided by 2. We're just putting this 2 over here as a matter of convenience. So minimize W transpose W divided by 2 subject to yi times W transpose xi plus b being greater than or equal to 1 over all n points xi in the training set. Here, what is yi? Yi is the label of the training point I. Now, what do I mean? What do I mean? Let us say this was your training data. Let us say your origin is over here. I give a label -1 to all the blue points. I give a label +1 to all the yellow points. So yi equal to -1 for these points, yi equal to +1 for these points, and therefore I can, if I multiply W transpose xi plus b with its yi, I can get rid of the modulus. Instead of saying minimum equal to 1, I am saying greater than or equal. This is greater than or equal to 1. You can confirm that this is a positive number, because whenever W transpose xi plus b is negative, I am giving it a label -1. Whenever W transpose xi plus b is positive, I am giving those points the label +1. Okay. So this is the constraint optimization problem that we are going to solve. And all of this happened. I mean, this looks like a simple formulation. It's, it's come about purely because of the peculiar scaling, like I said, that we engaged in for every hyperplane, in the space. So that was the reason for doing that peculiar scaling, because it leads to this sort of a simple formulation of the optimization problem. Okay. Repeating what I wrote on the last slide, we are now in a mathematical territory. We've sort of understood the logic behind formulating the problem in this manner. Now it is a matter of working out the math to actually solve this problem. And our problem is as follows. We have to minimize W transpose W divided by 2 subject to these constraints. Xi are our training points, yi are their respective labels. This, as is obvious, is a constrained optimization problem. So you have to minimize this subject to certain constraints, and these constraints are inequality constraints, as you can see, greater than or equal to 1. So these are inequality constraints. This is a constrained optimization problem with inequality constraints. And the method that we are going to adopt to solve this is known as the KKT method, named after researchers Karush Kuhn-Tucker. They came up with this method independently, and it is based again on forming the Lagrangian, like we did when we considered optimization problems with equality constraints. Here, because the constraints are inequality constraints, things will change a little bit. Let us see how they change. But this is the method that we are going to employ to find the solution to this optimization problem. Okay, now let us set up the Lagrangian and use the KKT formulation to come up with a quadratic optimization problem. Okay. So, couple of things before we start this exercise. The next several slides are mathematical. What we are going to do is we are going to apply the KKT conditions. Okay, so we will apply the KKT conditions. We will not derive them, or we will not go into the justification of how those conditions arise. We will just apply the conditions that are dictated by KKT to come up with what we need. Okay. So let's get started. We are going to rewrite the constraints as 1 minus yi times w transpose xi plus b is less than or equal to 0. Remember, we said that this quantity was greater than equal to 1. We've just rearranged the terms to make sure that this quantity becomes less than 0. In other words, this quantity is always negative. We introduce one Lagrange multiplier for each constraint. That means one Lagrange multiplier for each point in the training data, and we call it alpha i's. We'll say that alpha is greater than 0 for all I. I'll tell you why that is the case. Okay, the Lagrangian therefore becomes, this is the term that we wanted to minimize. So the Lagrangian is this plus summation I equal to 1 to n alpha I times the constraint, right? So this is, we are familiar with this. This is how we set up the Lagrangian. And because we said that alpha I is always greater than equal to 0, this term is always negative, and therefore the Lagrangian L is a lower bound at all times for the quantity that we wanted to minimize to begin with. So remember this, L is a lower bound for half of W transpose W, which is the quantity that we wanted to minimize. Okay, that's the reason for choosing alpha i's to be greater than 0. Okay, so you can expand this Lagrangian. This is just mathematical simplifications. You can expand this Lagrangian and you get half W transpose W, which is this, and then alpha I times 1, that is this, then alpha I yi w transpose xi, which is this term, and finally summation of alpha I yi b, right? So this is what your Lagrangian starts looking like once you expand it. Okay, we are going through a simplification process, by the way, and the eventual goal is to obtain a simple formulation that can be supplied to a quadratic programming package. That is our final goal, and we are going through these simplifications by applying the various KKT conditions. Now there are 4 KKT conditions, and I have written star WP here. WP means without proof. I am giving these conditions without proof. We are not going to get into their justification. We are going to only apply the conditions dictated by KKT as is. Okay. If you want a more detailed analysis of KKT conditions, I mean, that is available on the internet. For our purpose, we are going to apply those conditions. So let us see what those conditions are. I have copied the Lagrangian, expanded form of the Lagrangian right here. The first condition is stationarity. Stationarity means that the partial derivative of the Lagrangian with respect to the primal variables, which is our w and b, which are our original variables, it should be 0. Okay, so that is the stationarity condition. If you take the partial derivative of L with respect to w, you get this. So basically this is the w comes from here, and summation alpha yi xi comes from here, and this is what you get. And stationarity means that it should be a maximum or a minimum, which means that w minus summation of this quantity is equal to 0, which tells you the expression for w in terms of the alphas and the x's. So remember this is what you get by the first stationarity condition. By taking the partial derivative of the Lagrangian with respect to b, which is the other primal variable, you get b only appears over here. You get minus summation alpha yi equal to 0, or in other words summation alpha yi equal to 0. So these are the two equations that arise from the first KKT condition, which is stationarity. Okay, now let's go to the second and the third KKT conditions. Before that, as I just said, L, the Lagrangian, is a lower bound for the first term, because remember this is always positive, and this we said was always less than or equal to 0, less than or equal to 0. So together this is going to be negative, and therefore L is a lower bound on this, right? Now the way to get the tightest lower bound, is to maximize L as a function of alpha. Okay, is to maximize L as a function of alpha. So this is what we are going to try and maximize, right? So that L comes as close to this as possible. There are two conditions that result from that. First is called the primal feasibility, which says that the original constraints must hold. Now these were our original constraints, they have to hold. And the second is the dual feasibility. All multipliers must be non-negative. I just told you why that is the case. Together these ensure that this quantity is negative, this quantity is negative, and therefore L is a lower bound on what we wanted to minimize, right? Now if this is negative, you want to make, when you try to maximize it, you are trying to bring it as close to 0 as possible, in which case L will come as close to half of W transpose W as possible, right? So these are the conditions enforced by primal feasibility, and this is the dual feasibility. The fourth KKT condition is called complementary slackness, and what complementary slackness means is that a constraint should impact the solution only if it is active or tight. Okay, so a constraint should impact the solution only if it is active or tight. In other words, not all constraints are active or tight at every point in time, right? And therefore each multiplier satisfies this condition. This is known as complementary slackness. What does this mean? It means that if alpha I is greater than 0, then this quantity will be equal to 0. In other words, yi times W transpose xi plus b will be equal to 1. So either this is non-zero and this is 0, or this is 0 and this is non-zero. Okay, so that is what complementary slackness means. So what does it mean to say that alpha I is greater than 0? Alpha I greater than 0 means that yi W transpose xi plus b equal to 1, which means that the point lies exactly on the margin. Okay, such points are called support vectors. I will come to this in a moment again, but that is where the nomenclature for this mechanism comes about. Support vector machines, right? So this is either this has to be true, or if alpha is equal to 0, then this has to be non-zero, or vice versa. So if yi times W transpose xi plus b is greater than 1, then alpha I equal to 0, meaning that points that are further away from the margin planes do not affect the solution, because the alpha i's corresponding to them are going to be 0. This is known as complementary slackness. Now again, I have not justified why complementary slackness holds. I am only saying that it is a condition that is dictated by KKT, and this is how it applies to our problem. Okay, I am giving this condition without proof. Let's move on. So with the equations that we now have at our disposal based on the 4 conditions, let us re-evaluate the Lagrangian, right? So this was your Lagrangian. These were your stationary conditions, right? Stationarity, when you took a partial derivative with respect to W, equated it to 0, you got this. When you took partial derivative with respect to B, equated it to 0, you got this, right? So what does this mean? What does this do to the Lagrangian? When you substitute these conditions into the Lagrangian, you simplify the Lagrangian to just this. I mean, this is a terrific simplification, as you can see. And why does this come about? Let me explain. The first term directly comes from here. Because alpha y equal to 0 and b is a constant with respect to y's and alphas, b can be pulled out, and therefore this term goes away. What remains are these two terms. Now notice that w equal to summation alpha yi xi, right? So if I substitute this over here, if I substitute W in place of alpha I, yi, xi, summation over I, this essentially becomes W transpose W. Okay, so you have a minus W transpose W and you have a plus half of W transpose W, which leaves you with a minus half of W transpose W, right? So minus half of W transpose W, and once I replace W again with this, I end up with a double summation, one for the W's, one for the W transpose, one for the W's, and I am left with this term right here. So this is essentially half W transpose W, right? Because W is this. The double summation comes about because one of these summations is over W and the other is over W transpose, the other way around, right? So summation I going from 1 to n, summation j going from 1 to n, alpha I, alpha j, yi, yj, xi transpose xj. Okay, so this is what is left of our Lagrangian. Fair enough. Now KKT dictates that the way to solve, the way to optimize is you maximize, perform the optimization of the dual problem. So this is what was remaining of the Lagrangian, and you have to maximize it with respect to the alphas so that it comes as close to half W transpose W as possible. Remember, we said that the Lagrangian is a lower bound. You want that lower bound to come as close to W's as possible, so that the minimum of that is the same as the minimum of the Lagrangian. So you have to maximize this term. You have to in other words, you have to maximize this term, and the constraints are alpha I. This has only alphas. It doesn't have W's, it doesn't have B's, it only has alphas, and the conditions on alpha that we are aware of is that all alphas should be greater than 0 and summation alpha I, yi should be equal to 0. This came about from stationarity, as you know, right? So once again, you have to maximize this quantity subject to these constraints. Now this is a convex quadratic programming problem. It's quadratic because you have the products of two variables. You have alpha I, alpha j, you will have alpha I squares as well. So whenever there are whenever there are multiples of two variables or their squares, it's called a quadratic programming problem, and these conditions are of course linear in the alphas. You are going to solve this problem to get the best alphas. Okay, now here alphas are your variables. You already know that your W can be represented in terms of alpha, y and x. Your B can be represented in terms of y and alphas. So now the problem is to find the best alphas, okay, solve this quadratic programming problem and then get the W's and the B, right? So like I said, this is a convex quadratic programming problem which is fed to a program. There are programs available to do this. One example of such a program is known as the sequential minimum optimizer, and that will get you the values of all the alphas. So this dual optimization problem is to be solved for the values of alphas, which are the Lagrangians. Okay, assuming that the alphas have been found after you solved the quadratic programming problem, once you have solved the quadratic programming problem, you can get the W. You can get the W vector, which is simply summation of alpha I, yi, xi. Remember, xi are your input training points, right? Yi are the labels of those corresponding training points, and alpha i's are the ones that you have just found. And you are going to run this sum from I equal to 1 to n. The value of B can also be obtained by using any one support vector. You can take any one support vector S whose alpha S is greater than 0, and then by substituting you get B equal to Ys minus W transpose XS. Okay, so this is how you get the value of B. And finally, therefore, your classifier, once you have the W and once you have the B, you have the separating hyperplane, which is W transpose X plus B equal to 0. This is your separating hyperplane, and therefore the classification is simply f of x is equal to sine of w transpose x plus b. So if w transpose x plus b is greater than 0, that point lies on one side. If it is less than 0, the point lies on other side, and you perform this classification based on your hyperplane whose equation is w transpose x plus b equal to 0. Okay, so this is how the SVM problem is solved. Great. Okay, I have a few observations. Okay, there are a few observations. Firstly, the complementary slackness conditions. This was a funny condition that was dictated by the KKT, which said that alpha I times yi w transpose xi plus b minus 1 equal to 0. Okay, so either alpha is 0 or this quantity is 0, right? Or this quantity is 0. So one of the two has to be 0. Now, if alpha I equal to 0, then this need not be 0, which means that that particular point I is further away from the margin plane. Okay. On the other hand, if this is 0, if this part is 0, alpha I can be non-zero, right? Alpha I can be greater than 0. So what does it mean to say that this is 0? It means that that particular xi is actually a point that lies on the margin plane, and such points that lie on the margin plane are known as support vectors. They are known as support vectors. Okay, and therefore for support vectors, the alpha i's are non-zero, all other alphas are 0, and therefore the summation for w, the equation for w was summation I equal to 1 to n alpha I yi xi. Since alphas are 0 for points that are not support vectors, you can do this summation only over the points that are support vectors. In other words, points that lie on the margin plane, points that are on either side at a minimum distance from the separator plane that you have found. Okay? Okay. So to recap once again, the points on either side closest to the decision boundary are therefore called the support vectors. Now, where does this terminology come about? You can sort of picture it in your mind that the points that lie on this margin plane, you are calling them support vectors because they are sort of preventing this hyperplane from moving any further on this side. Similarly, this point, which is a support vector on the blue side, it is preventing this hyperplane from moving any further to the left. So in a way, they are sort of pushing the margin boundaries towards the decision boundary, not allowing it to go any further. Okay, not allowing the margin planes to go any further, and therefore they are called support vectors. So the point, this point is a support vector, this point is a support vector, this point is a support vector, etc. Okay, of course, support vectors are usually a very small subset of your total number of points in your training data, and therefore this equation, is basically the summation does not run over all training points. It runs over a very small subset of those, that subset being the points that are closest to the decision boundary on both sides. Okay, also called support vectors. So this is the first observation. I have another observation. The SVM provides a solution that generalizes very well. Remember, right in the beginning, in the first couple of slides, we said that the entire purpose of finding a decision boundary that maximized the margin was that it would generalize very well. That means the E out would be very close to E in. And if E in is 0, as is in the case of separable data, then E out would also be very close to 0. You would get a fantastic binary linear classifier. So to recap, SVM, the entire purpose of maximizing the margins was our belief that it would generalize very well, right? And that is indeed the case. What we are saying here, again I have drawn a diagram. This is the best separation boundary that you found. These are the two hyperplanes on either side that maximize the margin, that maximize this margin, and therefore this linear classifier is going to generalize very well. There is actually mathematical proof of this fact as well, okay, but just from a point of view of intuition, to build an intuition, why does this generalize very well? Why does having a high margin generalize very well? Well, the way to think about it is to go back to many lectures ago when we discussed the VC dimension, we discussed the growth function, we discussed dichotomies and so on and so forth. The fact is that when you insist on a large margin, the number of dichotomies naturally reduces. For example, this may be a dichotomy that is supported otherwise, but the margin for this particular dichotomy is very small. So if I were insisting on margin being greater than some quantity, some of the dichotomies would absolutely go away, right? Because for those dichotomies, the points are simply too close to the separator. This means elimination of several dichotomies, which in turn means that the growth function is reduced. Right? Growth function essentially captures the number of dichotomies, and the number of dichotomies is less if you insist on the margin being high, right? Reducing the growth function therefore implies a lower VC dimension, as you know, as we studied in the past. And what does lower VC dimension mean? Lower VC dimension means lower number of variables and therefore better generalization. Okay. So that is sort of the theoretical reason. I have not gone into the proof, but that is the reason why theoretically the SVM generalizes very well, because simply you are looking at a lower VC dimension. Okay. Again, I am giving a result without proof. The generalization result for SVM says that the expected value of E out, expected value of out of sample error, is the expected value of the number of support vectors divided by n minus 1. Like I said, the number of support vectors is a very small fraction of the total number of training points. N is the total number of training points. Therefore, this ratio is likely to be a small quantity, and which means in turn that the expected value of out of sample error is going to be a small quantity. So this is the generalization result. Again, I am stating it without proof. You can go back and look at the proof. It's available on the internet. But this is what the generalization result for SVMs is. This was sort of a hand waving justification that I had given. This is the generalization result for SVMs. Okay, so expected value of the number of support vectors divided by n minus 1, where n is the number of training points. Okay, so this talks to the question of why does an SVM generalize so well. Observation number 3. The Lagrangian in SVM versus the Lagrangian in regularization. Remember, long time ago we studied the idea of regularization, and at that time also we had built a Lagrangian. There is sort of a symmetry in what happened in that case versus what happens in the case of an SVM. Okay. What did we do in SVM? In SVM, we minimized the norm of W while constraining E in. How did we constrain E in? The in sample error, by saying that the in sample error has to be equal to 0, right? We said that, the hyperplane that we found, it should classify all the training data correctly because the data is separable, right? So we constrained E in to be actually 0. Right? And we minimized the norm of W. That is what we did in SVM. Now, what did we do in regularization? If any of you remembers, in regularization, we minimized E in. we minimized the in-sample error while constraining the norm of W. We said W transpose W equal to C, right? So we were constraining the norm of W and minimizing E in. That is the symmetry that I am talking about. Here you minimized W while constraining E in. In that case, you minimized E in while constraining W. It's just a sort of an interesting observation that I thought you should be aware of. Observation number 4. Observation number 4. Now, if you kind of stare at this equation that we got for W's, which said that W, my hyperplane, is summation over SV, summation over all support vectors, alpha I, yi, xi. Yi is a label which is plus minus 1. Alpha I was determined using the KKT. And xi's are my input points, right? So W is a linear combination of my input support vectors. Okay, so W is a linear combination of my support vectors only, right? Why am I saying that this should come as no surprise? It should come as no surprise for the following reasons. Number one, we saw the perceptron. There our algorithm was W new equal to W old plus y hat I times xi, right? For all points where y hat did not match the observation. So where the observation did not match the computation, for those points we included only those points, and we had this recursion, right? This was a recursion. So you kept adding multiples of xi to get the weight vector. When we did the binary linear classifier with the hinge function very long time ago, we got with the steepest descent gradient, we got an equation that looked like this, where again y was W, the weight vector, was constantly upgraded by adding multiples of the input xk. Okay, input xk, where the observed value of the observed value of the class did not match the computed value of the class. You can go back and see what this zk was, and so on and so forth. But again, you are doing like you're doing a linear combination of the input points over and over again in your recursion. So this is sort of in line with the same thing. SVN also does the same thing, except that here the linear combination is only over the support vectors. Now that is also fairly logical. I mean, the support vectors are the vectors that are closest to my final binary linear classifier, and it stands to reason that if I was trying to maximize the margin, it really makes no difference to me where the further away points are. I mean, instead of being here, this blue point could be over here. Instead of being here, this yellow point could have been over here. The margin, this would still have been the best margin, and it would not have affected my final result. So therefore, I feel that it is sort of intuitive that your final separator is simply a linear combination of only the support vectors. Okay, only the points that are closest to the decision boundary. So that is my observation number 4. Observation number 5. This is a tricky one. Okay. The question is, hopefully at this point some of you share this question. Hopefully some of you have been troubled by this question at this point. Why should we do this whole KKT business at all? Isn't there a better direct method of finding the best separator, right? Or is the KKT mechanism the best, the only way or the best way of finding this, this so-called best separator that maximizes the margins? Okay. Here is what I mean. Let's say this was your training data in 2 sets. It's linearly separable, right? All I really want to do is find the maximum margin, right? Find the maximum separation between these 2 clusters of points in a way. And surely there must be some methods of doing that directly rather than going through this whole KKT approach that we went through? Well, it turns out that, there are there are indeed methods that can get you directly to that point. One way of doing that is to find the convex hulls for the two classes. Okay, what do I mean by convex hulls? The convex hull is basically the outer boundary of each of your sets. Okay, so this is the convex hull for one group, this is the convex hull for the other group, and so on. Okay, not so on, there are only two groups. So this is one convex hull, this is the other convex hull. Given that these two are separable, you can find the convex hulls for both of these classes, and there would be a clear distance between them, because again, like I said, the two classes are linearly separable. There actually exist methods, numerical methods, to find the closest faces between these two convex hulls. So this is hull number 1, this is hull number 2, and there are actual methods, numerical methods that exist that allow you to find the closest faces of these two convex hulls. The method specifically, one method specifically is called the GJK method, stands for Gilbert Johnson Kirti method. Okay, so why don't we just employ something like this? Find the closest faces, and then find the equidistant separator. Wouldn't that be a simple, well, at least conceptually simple, intuitively simple way of directly getting what we want to get, right? So this is a valid question. Okay, and if this question troubled you, good for you, because this is a valid question, and you can indeed do this and get a solution without the KKT for linearly separable data. That means hard margin SVMs that we have been talking about. Okay, so KKT solution that we gave is not, it's not compulsory to use that solution. It is by no means the only way to get to the solution if your data is linearly separable, which was the case with this particular lecture. Okay, you could also do something like this. Why then did we go the KKT route? We went the KKT route because the KKT solution is extensible to accommodate non-separable data, or what we call soft margin SVMs. Okay, so in real life, it's unlikely that you are going to find separable data. Your data is most likely to be non-separable, and therefore we need a method. That sort of stays with some of the principles behind SVM, and makes it possible to apply it to non-separable data also. So you need techniques of that sort, and the KKT solution that we talked about in this lecture is extensible to accommodate non-separable data. I mean, the definition of margin, etc., will change, no doubt, because if it is non-separable, you are not going to have those clear margins that we have been seeing in this lecture. But there are ways to accommodate that kind of data, and the KKT solution is extensible in that regard, and therefore we studied the KKT. So in a funny sort of a way, we said that this lecture would be about soft margin SVMs. But really we came up with a technique that was intended to help, we said that this lecture would be for hard margin SVM. But in a funny sort of a way, we developed a method keeping in mind the fact that it would be extensible to soft margin SVMs as well. Okay, soft margin SVMs are going to be the subject of our next lecture, okay, where we will extend what we have just studied to non-separable data. Okay, how are we going to do that? A sneak preview. There are two ways of extending the hard margin SVM to data that is not linearly separable. Okay, we use something called a soft margin SVM for data that is almost separable. So subjectively speaking and proportionately speaking, if there are only a few points, okay, if there are only a few points that have sort of crossed over from one class to another, then we are going to employ a method called soft margin SVMs. Okay, and I call that almost separable because proportionately, subjectively speaking, there are only a few points that are sort of strayed over. Okay. On the other hand, we are going to develop a new technique called kernels. This is something that we talked about in the earlier lecture as well. We are going to use something called kernels for data that is badly non-separable. What I mean by badly non-separable means that it is not a situation where there are a few stray points that have crossed over, but you are going to really require some sort of a very non-linear separator, between your data points, okay, between your data points to do, to do your classification. So when your data is of that type where it requires something squiggly like this, it's badly non-separable, and we are going to use the technique of kernels to solve that sort of a problem. Okay, that brings us to the end of this lecture, and here is the summary of what we have seen. SVMs maximize the margin and therefore provide good generalization. This we saw in abundant clarity. Solution involves a peculiar scaling. It involves a peculiar scaling which simplifies the formulation and optimization. Now I want you to go back. And assume that instead of that scaling that we did, we scale such that all the vectors are unit vectors. That would be one type of scaling. And then sort of formulate your problem, and you will see that you have a lot more variables and lot more constraints. Okay, so the problem complicates if you do any other type of scaling, and this peculiar clever scaling allowed you to actually reduce the number of variables and reduce the number of constraints. I'll give that as an exercise at the end of the next lecture, but you should go back several slides and see why that is the case. The constraint optimization problem was solved using KKT method. It was solved using the KKT method. And the expected, this was very important, we gave this without proof. The expected out of sample error is proportional to the number of support vectors, which are few, and therefore it goes down with increasing training data. Okay, so this is the summary of what we studied in this lecture. It's not been a very long lecture, so thank you, and I'll see you for the next lecture, which will be SVM part 2.